Hello and welcome. Today we're tackling a problem on HackerRank known as equal. This is a medium difficulty problem. As usual, I'll go over the problem, give you some time to do it on your own, and then go over my solution. Here we go. Christy is interning at HackerRank. One day she has to distribute some chocolates to her colleagues. She is biased towards her friends and plans to give them more than the others. One of the program managers hears of this and tells her to make sure everyone gets the same number. To make things difficult, she must equalize the number of chocolates in a series of operations. For each operation, she can give 1, 2, or 5 pieces to all but one colleague. Everyone who gets a piece in a round receives the same number of pieces. Given a starting distribution, calculate the minimum number of operations needed so that every colleague has the same number of pieces. Given an array of 1, 1, 5, meaning that there are colleagues with 1 chocolate, and then one with 5 chocolates, and you can distribute 1, 2, or 5 pieces to all but one colleague. So if she gives 2 pieces, the first 2, then the distribution is now 3, 3, 5. And on the next round, she gives the same 2 people 2 more pieces. Then you have an equal distribution of 5, 5, 5. And it took 2 rounds of operations to do this. So the answer should return the number 2 for the number of rounds. All right, so that's it. I'll give you some time to do it on your own, and I'll come back with my solution. Good luck. All right, so first we're going to start out with the 3 operations. 1, 2, and 5. Put them to the side. So let's start out with example of 2, 2, 3, 7 as a starting point. We'll see some totals here, and so far no operations. Now we can first put the number 1 on each except for the third one, and that brings us to 3, 3, 8. And then we can add 5 more on top of the first 3 to get everything up to the same point, 8. And we see that everything's now equal, and we have a total of 2 operations. Now, what's interesting is that there's the additive property where the order doesn't basically matter. So we can add the 5s first, and then we can add the 1s after that, and it's the same thing, still 2 operations. Addition and subtraction are essentially 2 sides of the same coin. Instead of going up, adding a value to everything except for 1 is similar to subtracting that same value from that 1 that was being omitted. We can take the 7 and remove 5 from it. Similarly, instead of adding 1 to everything except the 3, we just subtract 1 from the 3. That brings it all in line. Everything's now 2, and we have still 2 operations. So it's essentially the same thing, just a little bit simpler. Let's go back and check out this operation. What we're essentially trying to do is bring everything up to the 7. The first step could be to add the 5s. Again, the order doesn't matter, but we go a little bit over, and so now our highest point is the 8, and then we kind of just bring everything up to the 8 by adding 1. That is kind of the idea of picking one value, the highest value, and then having that as essentially your target. If we're working with subtraction, however, now we're not targeting our highest value. We want to actually target the lowest value. Let's check out another example. Here we have 8, 4, and 13, and we'll keep track of the number of operations. In our example here, we're going to be saying 4 is our minimum. We're trying to subtract down to the value of 4. First, we want to knock out the largest value, in this case 13. We tried to take it down as much as we can, so we're going to use the 5. Then we can take out 2. Now the largest value is the 8. We take out 2 from there. Now we can take out 2 from the other, and 2 once more from this. And now we see that all of those values are on the same level. We are essentially done at this point, and it took us 5 operations to do that. So what's interesting here is we never actually changed this small value, the 4. That was our target, but you could recognize that there's sort of room for optimization here potentially. By lowering our target, we might be able to squeeze in some efficiency. Let's go ahead and just, for all argument's sake, lower the bar just by 1 and say our target is going to be 3, and we're going to need to try and bring all values down to that level. Same thing as before, we kind of knock down the largest value as much as we can. This time we take 2 5s out of it, and for the other side we take 1 5 out, and for the middle we still need to subtract 1 to get it down. We see in this situation it actually took 4 operations. That was less than the first time. We may be able to optimize further depending on what our target is. Let's check out another example. Here we have 13, 8, 5, and 18. For now, let's assume the target is 5, the minimum value, and we'll keep track of the operations. I'll just go quickly just to make it easy, but here are the number of operations for a total of 9 operations. All right, let's keep track of our operations versus our target. We're going to try a few of them. We're going to take our min value and we're going to subtract 1 from it to get 4, and that will be our new target to try out. So let's go ahead and reset. and try our target at 4. And here's what that looks like for a total of 10 operations. So this is actually less efficient than the first time. But let's keep going. Let's try our new target of 3, which is the min value minus 2. And we can see a total of 7 operations here. This looks much better than the first time. So we can see here by reducing our target, we're actually able to eke out some efficiency by essentially clustering and clumping together previous operations into just one. All right, let's keep going. Here our target is 2, and we see a total of 11 operations. Let's get a target of 1, which shows another 11 operations. We can see our optimal point here is when the value for our target is 3, which is our min value, 5, minus 2. Now, you'll notice that I didn't put much more on this table. Why not use the minimum minus 5? Let's check that out. If we tried the next level, which is to take our minimum and then subtract 5 from it, what do we see here? Well, we see that we get 13 operations out of that. Since the most that we can add, or in this case subtract, is 5, remember we can do 1, 2, and 5. When we take the minimum value and then subtract 5 from it, that's essentially like adding another operation on top of our count. When our target was 5, we see that we had 9 operations. When our target was 0, or min minus 5, we see 13 operations. You'll notice that there's a very convenient difference between those. It's 4. And why is it 4? It's because we have 4 columns in this situation. We have 4 colleagues that we're giving chocolates to. And that's where that difference comes from. So we don't need to go any further than this. We just need to try our min as itself, minus 1, minus 2, minus 3, and then minus 4. We don't need to go beyond minus 4. So here we have 5 possibilities we need to try out. And once we are done with that, we'll know our optimal count, and we can return that as our value. Let's go ahead and check out our most efficient operation, where the target was 3. We need to be able to calculate that number 7. How can we programmatically count these operations? So I'm going to go ahead and put side by side the total versus the kind of chopped up values. First, what we'll need to do is get the difference between each value and the target. So remember, our target is 3, so we're going to need to chop off the bottom 3. Given the 3 operation values that we have, 5, 2, and 1, we'll need to do some floor division and some modular math to get these counts going. We'll first want to deal with the largest value and extract as many 5s as we can out of each value. This will require some floor division. So we take each number, divide it by 5, and do floor division to get a whole number. Our first value has 2 5s in it, then 1, 0, and then 3. So let's take those and add them to the count. Once we've extracted all the 5s out, we want to extract as many 2s out as we can. This will require that we use the remainder from the previous division. This is where the modular math comes in. For the first example, we'll have 10 mod 5, which evenly divides, so there is no remainder. And then we would do floor division by 2, but of course it's 0, so there's nothing to really talk about there. Kind of the same situation for the second value. For the third value, we have 2 mod 5, because there was 2 left over. Then we do floor division of 2 divided by 2, which is just 1, and that will be added to our count later. And the fourth value, there's not much to do there. So let's add that 1 to the count, and we get 7. At this point, we would then continue on to get the operation for 1. Because it's 1, we don't really need to divide anything out. We could just take the remainder, and that value is the count for the 1s. So we would once again do modular math. We would take the value from before and then mod to that and to get the remainder. And in this situation, we don't have any. However, if we did, that value would be added to the count as well. All right, let's go ahead and check out the code. All right, here we are in JavaScript land. I will be sure to post the solution also in Python, so look for that in the description. But we're going to start out with a variable known as rounds. I'm going to be using this to select the minimum operation count once I go through all the possible iterations. So I'm going to start out at infinity because we actually are looking for the minimum value. So I need to start with like a larger number. That's all that is. Next, we're going to grab the min from the given array. This is a spread operation. If you're not familiar, it basically allows you to use this method on math.min to grab the min from an array. All right, next we're going to go through each target value. Now remember, this is going to require us to take the min and then subtract 0, 1, 2, 3, or 4. We don't need 5 or anything more than that because of what we mentioned before. So here is just a simple for loop, and I'm just going from 0 all the way up to 5. Then we're going to calculate the target, which is just the min minus whatever that n will be. We're going to set a variable called operation count, and we're going to iterate through the entire array. doing that modular math that we mentioned before. So first we're going to calculate the difference using the value, and we're going to minus whatever the target is. Then we're going to do the modular math for each value of 5, 2, and 1. First, we do the diff divided by 5, and we do floor division on that. Then we do this modular division to get essentially the remainder after you divide all the 5s out. And then we do division by 2 to get the number of 2s that are left over. And then lastly, we do the same thing with modular math, but all the 1s are being counted here. Then we add all those up and then add that to our operation count. By the end of this for loop, we will then have the total operation counts that it took to get all those values in the array up to, or I should say down to, the target value. Once we're done with the for loop, our operation count can be compared to the current variable called rounds, and the minimum value is reassigned. And then we'll have the optimal count for the number of rounds, and we will return that. All right, let's run some code. All right, that looks good. Let us submit some code. Hey, all right, very good. All right, let's check out some time complexity. First, we have this for loop up here, which you might think, oh, that's big O of n because it's a for loop. Let's keep in mind what we're doing here. We're iterating from 0 all the way up to 4. And that's always the case. No matter what the size of this array is, it's always going to be 0, 1, 2, 3, 4. So that's not changing. That's big O of 5, or I guess technically it's big O of 4, if we want to be technical about that, which is constant time. So that's not a real consideration. Then we are going to go through each element in the array. That is big O of n, where n in this case is the size of the given array. Now that is technically being looped through 4 times, but given how time complexity works, we drop constant, so it's still going to be big O of n in the end. All this stuff is math, so we don't need to worry about any complexity there. And we have a total time complexity of big O of n. All right, folks, if this is the kind of content you enjoy, please make sure to like, subscribe, do all the good things, and I'll see you next time. Take care.